In the last lesson, we talked about air masses. We talked about where they came from and how an air mass is that area that has a common temperature and amount of moisture in the air. And so as those air masses move around, that's where we have fronts. And fronts are what cause storms to happen. And so the front is just that boundary between the two. And the front always is described by the air that's behind it. So when we say we have a warm front, we're talking about the air that's behind it that is warm. So a warm front is an area where it moves in. It's a warm air mass that moves into an area and displaces the cold air. Cold front is just the opposite of that. The cold front is the big mass of cold air. So if it were 70 degrees here today and then tomorrow a cold front came through, it would drop the temperature down to 50 degrees or something like that because the air behind it, the front, is colder. Sometimes we do get long lines of thunderstorms that happen in front of the cold fronts because when the cold front moves in, and we'll look at a picture of this in just a second, it's kind of like this big wall of cold air moves in and it forces air up really quickly, and that's why we get thunderstorms. We don't get that when we have a warm front. The warm front, we tend to get we get our stratus clouds, right, which are heavier, darker clouds. This has to be a really warm, moist air mass moving into a cold area in order to get some of these nimbostratus and stratus clouds. Here in Arizona, usually when we have a warm front that moves in, we tend to get these thin, wispier clouds, maybe a little bit of light rain, but we don't generally get a lot of rain out of warm fronts that come in. Just because our area is so warm anyhow, there's not that big of a temperature difference when the warm front comes in. When the cold front comes in, it's an entirely different story. So on your notes, you have a place for just a little sketch. It doesn't have to be hugely detailed, but you do need to have the slant to the line is important because the warm air is just going to slide over the top of the cold air. So it's not a real severe line going up. You can see that it's a very gradual thing, and that's why we only get the light rains here in front of it. Here behind it, we get a little bit more. We've got a bit more moisture, okay, in this area in the warm front back here. But up along the leading edge of it, we tend to get the smaller clouds. We don't get as much rain. But you do want to have on your sketch where the warm air mass is, where the cold air mass is. So our cold front, on the other hand, moves in like this big, like the warm air mass moved in kind of in a wedge shape. The cold air mass comes in as a big block. And so because it comes in so severe into the area, it pushes this air up really fast. And so that warm, moist air just gets shoved up and it cools down really quickly. And that's why we tend to get more severe weather. You can see we get our thunderstorms out of this. We get our tornadoes out of this. This is where we're going to get significant storm activity out of this. So once again, you're going to draw your sketch. Look at the difference in the shape of the front and how it's pushing that air up really fast, causing a lot of rain. Precipitation happens in heavy spurts when we come in with a cold air mass. This is exactly what happens during our summer monsoon time. We have some other kind of fronts. So we had warm fronts, which is an area of warm air, right, coming in. We had a cold front, which is the area of the cold air coming in. We have stationary fronts, which is where usually there's not as big of a temperature difference between them, so they just kind of sit in one place. So if you're sitting on the side where the cold air mass is, it's going to stay cold. And if you're sitting on the side where the warm air mass is, it's going to stay warm. And if you're sitting close to the middle, then it's going to continue raining. So stationary fronts just kind of, they're static, and whatever happens is happening. Like whatever was happening continues to happen. The occluded front, though, is where we have a cold front that moves over a lot faster than a warm front, and it hits into another cold front. So you've got your big cold front coming in, you've got your warm air mass, right? This is a warm front on this side. You've got your warm air mass, but this cold air is moving much faster than the warm air was. So it kind of squeezes it out, and as it does that, it squeezes that warm air up on both sides, and so you get rain on both sides of the warm air mass. And as that cold air gets even closer, now we get really heavy rain because now the entire air mass is getting shoved up into the air. This can happen for a long time. Okay, so the way that our fronts move around is they're attached to areas of low pressure. So we said that low air pressure is when the surface of the planet is getting warmed up and the air is rising. It can happen because of that, or it can also happen because of collision. But the low air, the low pressure, is where we're going to have what's called a cyclone, and the high pressure is an anticyclone. You don't have to worry about those terms so much, but we do want to remember which way the air moves around an area of low pressure and an area of high pressure. On our isobar map, remember we saw there was an H and there was an L, and we looked at how close together the lines were. So as we're in an area of low pressure, our lines on our isobars are going to be a lot closer together. In our high pressure areas, they're going to be much further apart. So when we're looking at which way the air is going to move around a low pressure system, the air is going to move counterclockwise. And it's important for us to know that because that's going to tell us which way the front is moving, so we can predict then what the weather will be like in an area because we know which way the air moves. And then around the high, it moves clockwise, and so once again, we can tell what it's going to be like in areas. Now, there's no fronts ever attached to a high. Our fronts are only ever attached to lows. And so we know that all of our storm systems are always going to be moving in that clockwise pattern. So here we're looking at a low. Here in the center of your screen, you can see that the air is spinning around here. So we've got different movements of air. We have the movement of air because of the Coriolis effect. We have the movement of the air because of the global winds, and then we have this movement of air because of air pressure. Remember, we said all those things combine together to tell us which direction the wind is actually going to move. There are some times when one of those factors, excuse me, will have a stronger influence on the direction that the air is moving. So in here, in our cyclone, we've got our airs all moving around in a counterclockwise motion around the low. So we know that if there's a storm over here, that it's going to move this way. And if you're over here, then you're away from the storm, because not only is the low, the air is going to be spinning this way, but it's also going to be moving the direction of the global winds. So the low is going to move off in this direction because this is in the westerlies, and so the air blows from the west to the east. This is just another picture of what's going on. So in our area of low pressure, right, the air is coming into the area of low, and it's going to rise up. We get our clouds, right, because warm air rising cools, condenses, and we get rain. We have subsiding air, which is where the air starts to come down to the surface. It's an area of high pressure because all those air molecules are getting squashed closer together. So when we look at where do we get storms, we expect to see storms around areas of lows, not around areas of high, because in a high pressure system, the air is getting pushed down, and as it gets pushed down, it heats up as it gets closer to the surface. And we know that cold air doesn't hold as much moisture, so it's up high in the atmosphere, it can't hold as much moisture up there. As it gets pushed down and it heats up, now it can hold more moisture, so we don't get clouds forming, because the sponge got bigger instead of the sponge getting smaller, if we go back to my analogy of before. In our area where there's low pressure, remember, we're going to go back a slide here. In our area of low pressure, as this warm air is rising, remember the air is cooler down here, or it's warmer down here, and it's cooler up here, and this warmer air can hold more moisture. So our sponge is bigger. But as the air rises up, it's like the sponge got smaller, and now the water starts to come out of it, and that's why we get clouds forming. If you don't get clouds forming, you can't have storms forming. So here's a cyclone. Hurricanes and cyclones are not always the same thing. A cyclone is just any storm. It could be forming over land or over the ocean. A hurricane is a type of cyclone. We look at the way our cyclones move across the United States. Once again, we're moving from west to east because we're in the westerlies. The storm track here is the jet stream. It follows the jet stream. So depending on which way that current of air is moving, if it's staying up high, then the storms will be up high. If it dips down low, sometimes it dips way down here into Arizona, goes across this way. And that's when we get our storms. So we get our thunderstorms with the cold fronts, associated with the cold fronts, because we get that big mass of cold air that moves in, it pushes up the air really quickly. We get that updrafts of air, and we get heavy rains and hail, which we're used to getting here in the summertime. We're not the only place in the world, though, that it happens. Actually, I think Australia gets more lightning strikes than anywhere else on the planet, if I remember correctly. And that's just because there's lots of moisture. So there's lots of instability, there's lots of thunderstorms happening. Here's what our thunderstorm looks like. So our cumulus cloud, our mid-level cloud, right? Our big puffies. We've got air moving up into the cloud as the air is rising. It starts to develop and get bigger, and as it's getting up higher, it starts to cool, and that's why we start to get this downflow. And with it, it pulls that water down, that water, that droplets that have gotten bigger. And because we're looking at right now, if we assume that we were looking at a warm air mass, then we would be looking at our collision coalescence, right? That made our raindrops get bigger. And then once it's reached its biggest height up here, now it just starts to kind of break down. And it starts to, everything starts to move down through it, and we get some rain out of there too. We can get hail in both of these, in both of these stages. So a tornado happens because we've got the meeting of two air masses. We have a continental polar air mass coming down from Canada that's cold. We have a maritime tropical, or an MT, air mass that's coming up from the Gulf of Mexico. And they meet over the midwestern part of the United States. And then when they hit one another, okay, we've got a lot of instability going on because we've got really cold air meeting really warm air. And this is why they happen in the springtime, okay, when it's still really cold up in Canada. And then because of the global winds, we get a twisting action. And so that's why we get tornadoes over the midwestern part of the United States. It's also because it's really flat. Excuse me, and so there's not a lot of mountains or anything like that to produce friction to change the direction of the air. So we've just got this big flat area where the two air masses collide and hit one another. CP and MT hit one another, and the colliding result can end up in tornadoes. So we measure our tornadoes using the Fujita scale. It's based off of how much damage is done by the tornado itself. We have very infrequently, but it happens sometimes, we do get some tornadoes here. Really, with a tornado, you want to be in the center of the house. You want to be near plumbing somewhere where you can hold on. If you have a cellar, which unfortunately we don't have a lot of cellars here, you want it getting down under the ground, and this one is a good thing as well. But once again, we don't really have that here so much. Tornado Alley, they call it that just because that's where the air masses meet, and so that's where most of the tornadoes happen. So the CT air mass, the continental polar air mass comes down, and it's meeting the maritime tropical that comes up, and that's why they happen in this band across here. And there are some times when, if you watch the news, you can actually see the leading edge of the front when they show where the rain band is. You can actually see a very well-defined edge of the front. Even if they don't have the front on there, you can just see that edge, that leading edge, where the rain is really hard and severe. And that's where the two boundaries are with the air. So our Fujita scale is a 0 to 5 scale, and it's all based on wind speed. And then we look at the intensity on what kind of damage typically happens with that. F5, we've had a few in the past few years, in Oklahoma in particular, that pretty much it just destroys everything. So we can have very light ones, just some little damage, things broken, to, uprooting of pipes and stuff that were sunk down in concrete, just depending on how strong the tornado was. So our hurricanes only happen during certain times a year. We have to have the ocean waters in the Atlantic off the coast of Africa have to heat up. So they are in the trade winds in that area, and so the winds are blowing from the east to the west. And as they blow, it blows that area across the surface of the Atlantic. The Atlantic is warm, and so there's a lot of evaporation occurring, and so it gains a lot of moisture in the atmosphere, and that's where our hurricanes come from. Hurricanes are a little bit different than tornadoes in that they have a well-defined eye. So the center of a tornado We're not entirely sure what it's like because getting accurate measurements and readings from the inside, I'm sure a lot of you have seen the disaster type movies where they have theories about what it looks like in the middle of a tornado. We do know it's not still in the center of a tornado like it is in the eye of a hurricane. So the eye wall is dangerous in the hurricane, as is the storm surge. Because there's so much wind that's involved here, it pushes the water itself, and so it actually pushes taller waves towards towards landfall. So if you've seen, it's kind of getting kind of old now, but the movie Day After Tomorrow, uh, in part it was kind of towards the beginning where New York was going to get swamped in with water, and they showed this big wave coming in, and that was the storm surge that was coming in front of this giant storm. And while that was obviously a dramatic effect for Hollywood, the storm surge with Hurricane Katrina that happened in the Gulf of Mexico is actually what did more damage to New Orleans and some of our coastal towns, because the storm surge actually, the winds pushed the storm surge up over the top of the levees and flooded it and flooded the towns. So we do have an eye. It depends on how big the hurricane is, about how big that eye is, but it's relatively calm. The eye wall, it's really the winds are really strong around the eye wall itself, so that's pretty dangerous area to be. So you've got subsiding air, which is why it's calm, right? We say when air, it's an area of high pressure that's in the middle of the storm. We've got a lot of swirling that's going around it, and it happens in bands. So you can get hit over and over and over again by the storm. So we look at the hurricane intensity with what's called the Saffir-Simpson scale, and I'll show you that in just a minute. We talked about the storm surge already. So once again, it's a 1 through 5. They're called category 1 through 5 storms. And once again, we're looking at wind speeds again. You can see the wind speeds here, though, not nearly as much as they were with the tornadoes. So our category 5 is only about half, 2/3 to half of what F5 was on the Fujita scale for the tornadoes. So, but we're still looking at a storm surge of greater than 5.4 meters is pretty significant. A meter is 3 feet, so we're looking at, above 15 feet.